Welcome back to Linear Algebra by Linear Algebra Dumbbell by Sheldon Axler. So I've been procrastinating on this for too long, and there are days when I just stare at this question 4 or 5 and it doesn't make sense to me, and I haven't moved past a single page. So I think I gotta do this now. So even though I haven't solved anything past 4 in my head, I think I'm just gonna wing it and just do these questions on the spot and come up with the best explanation I possibly could and move past it, because I don't have time to waste it's not a waste of time, but we're already at chapter 5 and this is still chapter 3, so I gotta move. Let's look at question 1 for a second here. So suppose you got a linear map from U to V, and similarly you have a linear map from V to W, and they're both invertible. Then what I want to show is S composed with T is invertible as well, right? I think this is reasonable because, and here's the reason. Let's say that the inverse of T is T minus 1 and the inverse of S is S minus 1. In this book, they define inverse as double-sided. So T minus 1T is equal to the identity. Let's say this in the map U, and T composed with T minus 1 is the identity, let's say, within the map V. So what you want to do is you just want to say that, just follow along with the compositions, right? And what it means for T minus 1, S minus 1 to be the inverse of ST is just that when you compose it on the right-hand side versus you compose it on the left-hand side, it both brings you back to the identity map. Of course, it's the identity map of different regions, but it's the identity map nonetheless. So I was thinking about, it's S composed with T. That's my bad. Yeah, I was staring at it and it's like, that doesn't make sense. So the thing with composition with linear maps is they are associative. And whenever people talk about the associativity of matrix multiplication, if you think about it in terms of linear maps, it makes a lot more sense because composition is associative, just by the definition of it, right? So this way, if you think about it, what this is going to turn into is T minus 1, S minus 1 composed with S, T, right? And let's say if you put in some arbitrary U inside the set U, what you're going to get back is some arbitrary V inside the set V, and this is the identity over V. So what you're going to get back is still the same V inside that V, and T inverse of that V will bring it back to U. So this works for arbitrary U. So this in fact is the identity map over U. And if you do it the other way around, and since ST is a map from U to V, that this is the identity map of U, makes sense. But you want to do it the other way around, with the composition ST, T minus 1, S minus 1, right? It's very symmetric, so I won't go through that. The argument is essentially the same, but you swap at S and T is what you would do, I think. Question 2, suppose V is finite dimensional, and let's suppose that it has a basis, right? Because whenever you think finite dimensional, brain should automatically establish a basis of such a finite dimensional space. It's a freebie, right? Whenever it's infinite dimensional vector space, you might be in trouble because you're not always guaranteed to have a basis, I think. I'm not sure. I'm not too clear on that. My professor talked about it in class, but look, I like the guy. If I was his colleague, which I don't think I will be because I'm not talented enough, if I'm his colleague, I would enjoy talking to him all the time. But as a professor, he's not very good. Yeah, but he's really friendly if you talk to him in office hours. That's all I can say. All right, so dimension of V is greater than 1. Prove the set of non-invertible operators on V is not a subspace of LV. Right, that's why I'm doing all this, right? If I was confident in the class, I probably wouldn't be doing all the exercises in a bloody book and posting it on YouTube to monitor my progress. That'd be maybe a bit overkill. Yeah. So we want to show the set of non-invertible operators in V is not a subspace. So by non-invertible operator, I thought about it. They probably want you to map one of the elements of the basis to 0. That's what they want, because non-invertible means kernel is not trivial, or kernel is not just a 0 element. So if you map, let's say there is a non-invertible operator that transforms T1 of V1 into 0, and also another one that transfers T of V2 into 0, and then the rest of the operator is just the identity. I don't know how many other basis vectors there are, but the rest is the identity. And then what you have here is T1 of V1 plus T2 of V1 equals to V1, and T2 of V2 plus T1 of V2 is equal to V2. So in fact, that I think you are no longer non-invertible, because now you cover the entirety of the space of V within your linear operator. The sum of your two non-invertible operators is an invertible linear operator, is what I think, right? Yeah, because nothing really belongs in the kernel anymore, because the rest of it will go like T1 V3 plus T2 V3 is just 2 V3, and that's perfectly fine. There's nothing wrong there. Just mapping T1 plus T2, the function T1 plus T2 maps V1 to V1, maps V2 to V2, and everything else to twice times that thing. And this is perfectly what you might call it, bijective operator. So suppose V is finite dimensional and U is a subspace of V, and then S is a member of the linear maps from U to V, and then prove there exists an invertible operator such that so this is an if and only if question. So what you want to do is go one side and then the other. So let's say if there exists a linear operator so that we have another linear map, then T of U equals to S of U for every U and U if and only if that's the part you have to prove. Then S is surjective, S is injective. Okay, let me see what's going on here. So U is a subspace of V. So I think what you're looking at here is, because T is an invertible operator, then the kernel of T must be 0, because if you're an invertible operator, you're operating within V from V to V. That means range of V must be equal to V itself. Since you're invertible, you must also be surjective and injective on the same thing. So, well, like, without even this complication, invertible just straight up means kernel is 0, because if you're not injective, you can't invert it, right? Just in the general case. So it just implies that T has kernel of 0, right? And since T of U is equal to S of U for every U in the set U, then S must also have kernel 0. Because if it has anything more than that, then T must also have something more than that in its kernel, which is not going to happen. So S has also a kernel of 0. And since S has a kernel of 0, then it's clear that S is injective. But so now you want to go the other way around, which I suspect is much more difficult, because now you have to construct the T, right? So suppose that S is a linear map from U to V, and it's injective, right? So we got that, and we want to construct T construct T such that T of u is equal to S of u for every u and u, and T is invertible. Is this possible to construct? By the question, it's saying like if you got the previous condition, then you must be able to construct it. But let's see if it's even possible. It should be. So within the domain of u, like the map of T restricted to the domain of u, because it's supposed to be over the entirety of v, but we can put it in u for now. Consider u for now. It's just going to follow precisely what S does. And it's going to be perfectly invertible inside of this because it's injective and surjective. Or not surjective, it's injective. And so it doesn't violate any of the invertibility stuff. But if you move on to the rest of it, so what you probably want to do, since v is finite dimensional and u is a subspace of v, that means u is also finite dimensional because it's spanned by the basis of v. And then you can reduce the basis of v to a basis of u by removing arbitrary vectors which are linear combinations of the basis of v. Then u must also have a basis which is finite dimensional. And then what you have then is, in fact, u is a finite dimensional vector space which can be spanned by a basis which we can arbitrarily construct. Let's call this u1 through uk, and then we'll extend it to a basis of v. So we'll extend it to a full basis in v. Vk plus 1 up until, let's say, Vm. So if you extend the basis of u into the basis of v, what you're going to get is you want probably to map the rest of the bases which are in v but not in u. You want to map these basis elements to the identity. So what you're probably going to notice is if, but a more straightforward way of doing this, perhaps not so convoluted, is if v is inside v but not in u, then T of v equals to v, right? But if v is in u, then T of v is equal to S of u, or S of v rather. And this is your map construction. I think this is perfectly injective for the reason that the identity function is what T is when restricted to v minus u. That's perfectly fine, right? That's perfectly injective. And also when T is inside the space u, then you restrict it to S of u, and S of u is already S was already an injective map. So the two parts are injective, and the overlaps don't cause any loss of injectivity because their ranges don't overlap. So, or actually no, maybe that's a fact claim. Because S does map from u to v in general. Okay, yeah, no, this is a mess. Yeah, you cannot do that. You need to be more careful about the construction. So what you want to do is say the range of S, generate a basis of that in V, of which you will get V1 through Vk, let's say. And then S itself, let's say the basis for it is S, or not S, I mean, the basis of U is U1 through UK. From the range of S, generate, or extend rather, a full basis of V. So Vk plus 1 to Vn. So this is what you want to map the elements which are in U, which are in V but not in U, into. We'll call this a different basis. W k plus 1 through Wn. So you want to map this here, and then your injectivity is shown. Because you mapped U1 through UK to V1 to V through Vk, and Wk through Wn to Vk through Vn, now this is clearly an injective map. So that's fine. If you want to think about this in terms of diagrams, which I usually like to draw some diagrams because all the algebra gets a bit confusing after a while. So you know t t minus u e, and this maps to something in here. This maps to something in here. This is injective, and so is this. You can simply say it's injective because if it was not, then a linear combination of the basis elements are in V but not in U will form a non-trivial linear combination, which is not possible because they're basis elements, which means they're linearly independent. So then you can show that it's indeed an injective mapping. Of course, you can also show it's an injective mapping, but saying it's mapping from a dimension of, let's say, n minus k to another dimension of n minus k, and it's surjective. So then it must be injective as well, because surjectivity means their ranges are equal. The range is equal to the dimension of the output, which means the kernel will have 0 dimension, so that's fine. So that means you can essentially actually even establish a bijective, but so that's too strong. You don't need that. I'm probably overthinking here. Question 4. Suppose W is finite dimensional and T1, T. Yeah, so this is where I got stuck for 2 or 3 days because while I was being bogged down by other subjects of trying to pick up this and think of this and pick up the textbook. Must have done it for a dozen times. And I thought about this, and I just, like, the concept is interestingly simple, but like there's no good way to explain it in words. Like, it's terribly difficult to like demonstrate concretely. So let's say you have two linear maps from V to W, and you want to show the null space of T1 is equal to the null space of T2. Like, if this is true, then you wish to establish that there's an invertible operator such that T1 is equal to S of T2, right? You want to do this. So I think needs to happen is you need to somehow show that null space of T1 equals null space of T2 allows you to indeed establish this invertible operator. And this is quite believable from the perspective that S is a mapping from the range of T2 into the range of T1. And in fact, these two should have the same dimension from the null space of T1 being the null space of T2, which means the dimension of the range of T2 should be equal to the dimension of V minus the dimension of null space of T2. And the same situation goes for T1. It should be dimension of V minus the dimension null space of T1. So then the ranges, since the null spaces have the same dimension, the ranges should have the same dimension as well. And then, if the ranges have the same dimension, what you do is establish a basis for each and then establish a linear map that maps the basis of one to the basis of the other. The coefficients are arbitrarily assigned, they don't matter. You can give them all ones for all I care, but it should work that way. But like, this is very hard to concretely pin down in terms of words, because even though this is a valid way to think about it, it's not a concrete proof, right? So if you were to write this on your homework, you maybe only get half points for it. But I'm not here to do homework. I'm here just to do some random exercises and gain knowledge, hopefully. And try not to confuse myself in the meantime. So you will establish such a invertible operator because it is in fact mapping from a basis of dimension, let's say a minus k, to another basis of dimension, forming a vector space of dimension n minus k. The bases have the same dimension, mapping one to the other. It's completely injective because you don't lose any of the range. It's surjective. For any linear combination of 1, you can use the basis elements to get the appropriate input. So it's surjective, which means that the kernel must be dimension 0 once again. And with dimension 0 kernel, which means you're injective, and surjectivity as shown. that's sufficient to say you are, what's it called, invertible. I think, in fact, that this may even be too strong for invertibility. Maybe it is, maybe it is not. Let me see. I know there is an invertibility definition for operators, but I'm not sure if there is one for linear maps in general, because operators are a heavily restricted set of linear maps. Yeah, invertible map has a unique inverse. That's not saying much. Yeah, invertibility is equivalent to injectivity and surjectivity. There, that's saying much more. So what I just did is correct, because injectivity and surjectivity. Yes. You prove the theoretical existence of S, which is sufficient for this question because it does not ask you to actually establish such S, right? You don't need to give the example. But if it ever falls on you to, the burden falls on you to establish such an example, you just need to map the basis element of one into the other, because it's arbitrary elements of your choice, arbitrary coefficients of your choice. So here, if you have this, and you want to go backwards, you want to show no space of T1 is equal to no space of T2. And S is invertible, of course. This is not quite easy to show, I don't think. And it takes a bit time to think about. So, you know, if there exists a invertible operator, and let me think. Well, I think one thing you can say is that their kernels are the same, right? Kernels of T1 is equal to the kernel of ST2, and I think it was shown in the previous exercise what the kernel of the composition of linear maps was. I have forgotten it, but I haven't forgotten that there was a result like that. Yeah, I think it's somewhere around here. Oh, it's not even that concrete. Yeah, it's quite loose. So, but I think that might be enough. So, the dimension of the null space of T1 is less than or equal to the dimension of the null space of S plus dimension of the null space of T2. But since the null space of S is 0 by injectivity, that directly means the null space of T1 has less dimension than the null space of T2. That's proof 1. Or I mean that's inequality 1, that's not the proof, sorry. But you want to go the other way around and say that you want to use the range probably, the composition, the range of the range of compositions. Dimension of range T1, which is equal to v or n minus, if you call the dimension of v to be n, v minus dimension of t. This is sorry, I meant to say that. Right, yeah, because I skipped a step. There was supposed to be a dimension of the composition of S and T2 here, but that's okay, it's the same. And then the range has the same, but I would include it here in this step. Dimension of the range of S composed with T2, let's say. And that's less than or equal to the dimension of the range, the minimum of the dimension of the range of S and the dimension of the range of T. Or in this case, it would be T2, I suppose. But like, I'm not quite sure which one of those would be less, because it's unclear what the relationship of U compared to V is. I think here if you flip it around, then what you get is, because you want to plug in a minus dimension of null t1, and minus dimension of null t1 is greater than equal to no, but then you get greater than and less than. That's not very advantageous. Okay, so if dimension of range t1 is less than something, then dimension of null space of t1 is going to be greater than and minus that min, whatever this is, right? And then let's just pretend optimistically that the range of S is greater than the range of T2. No, I don't think that works. Yeah, no, this is not great. No. We've shown that the dimension of null space of T1 must be less than that of T2, but it's not enough. But in fact, if the dimension of the null space of T2 takes on greater value than dimension of null space of T1, then it will map more dimensions to 0, which S cannot successfully recover. So in fact, dimension null space T2 cannot be strictly greater than the dimension of the null space of T1, so they must be equal. I mean, that's a very strange way to say such a thing. I was hoping for something cleaner, but I think that will do. I think like the most straightforward way I was thinking is that if there's an invertible linear, if there's an invertible operator, and the operator maps from the range of T2 into the range of T1, and the range of T2 and T1 must have the same dimension, because for S to be an invertible operator, it must be surjective, which means the range of S over T2 over S over the range of T2 must possess the same dimension as the range of T1, which means and then similarly the dimension of the kernel kernels must be equal as well, right? Or did I think of something stupid? Maybe it's not even that like screwed up. Let's imagine that there exists T1v 0 where T2v is not equal to 0, right? So v is in the kernel of T1 but not T2. So can this really happen? I mean, if this really happened, then T1 of v will be 0, but T2 of v will be S of some not zero number. If it's S composed S on some not zero number, is not going to be 0 because the kernel of S is 0, so it's got to be mapping all non-zero numbers to something else, which means that really 0 has got to be v has got to be in the kernel of T2. Otherwise, there's no way for S composed with T2 to be 0 either. Let's try the other way around. If some value is inside the kernel of T2, then T2 will be 0, and S composed with T2 will be also 0 because S maps 0 to 0 as a linear map. And T1 of v, if it is not 0, then that doesn't make sense because T1 is supposed to be equal to S composed with T2, so it's also got to be in the kernel of T1. See, that was like 200% easier. See, it was supposed to be clean up like that on the first try, but I think the second try is good enough for me. So suppose V is finite dimensional. And you have T1, T2, which once again belong in the set of linear maps from V to W. And you want to show that range T1 plus equals range T2 if and only if there exists an invertible operator. Okay, so it's like a very similar question. It's a very similar question. So you want to show that if this is true, then you can construct, or not that you can construct, exists S such that T of S T1 equals to S T2. So here, since once again that anything which is in the input of S must be in the range of T2, right? But maybe that reasoning is a bit loose. But if you construct a basis for the range of T2, and then what you might get is V1 through Vn minus K, for example. And then what you have is that, let's say, anything S maps from, let's say S maps from some arbitrary W, then that W must be a linear combination of the range, right? The range of T2. So then, and what it maps to, oh wait, what am I doing? No, that doesn't make sense. Hold on. Okay, hold on. So exists S, which is invertible, so that T1 is equal to T2 times T2 composed with S. So for this to be true, it must be that for arbitrary V in big V, T1 of W is equal to T2 composed with S of W. And what that must mean is that somehow this S of V doesn't change things, I guess. Or no, it should change things. Let me think. Because T1 and T2 have the same range, but they just might not map the same inputs to the same things in the range. So what might occur is that, but if you establish a basis for both the ranges, call it V1, or maybe like W1 through WK, then any result in T1V is expressed as a linear combination of this thing. And S is a member of the operators of V. Yeah. I think that's a bit rough. Yeah, but since T2 and T1 have the same range, there must exist V prime such that T2 of V prime equals whatever this output was. And then S of V is just defined as V prime, right? So for every such arbitrary V, you find T1V, note the output, note that there also must exist V prime such that T2V prime equals that output, make S on such arbitrary V produce output V prime, and then you've constructed the operator, but you have yet to show that it is invertible, right? And so to show that it's invertible, you must show that it's bijective. And since this is heavily designed from T1 and T2, you want to pay close attention to that as well, right? So you cannot have, so let's say that it's not injective, that means S of V1 equals to S of V2 equals to V prime, right? Where V1 is not equal to V2. Then what that must mean is that T1 of V1, because if you think about it this way, the definition sort of says that T2 of V prime, that must be both V1 and V2, because that's how we derive this, I think. Let me try to think about this for some more. No, that's not what it means. That is not what it means. Hold Okay, so what this means is T1 of V prime. Hold on. I don't get it. Shoot. Oh, wait, I think I see it. Okay, got it. The system I did was a bit convoluted, so doing anything within this system is a bit weird. So that we know that T1 of V1 equals to T2 of S composed with V1. So then T2 of V prime is equal to T1 of V1. But T1 of V2 also is equal to T2 of V prime. So T1 of V1 equals to T2 of V2. But in fact, this cannot. Can this happen? Oh, hold on, it might. Why not? Oh, okay, maybe I have designed this S incorrectly. No, but there's no other way. This is the only way you can design this S. No, I refuse to think like that. Yeah, I think I'll maybe be back, but this question is a bit puzzling. I'll give it another try. But without all this jargon, trying to think if it makes sense. Because if S is an invertible operator, it preserves the dimension of the input and the output. So if you put the operator into S, it's not gonna squeeze anything or produce any kernels whatsoever. And then the kernel of T2S is just equal to the kernel of T2. Because previously, I think, as we saw, that the kernel of the kernel of the composition is equal to kernel of 1, is less than equal to the kernel of 1 plus the kernel of the other. But since the kernel of one of them is just 0, the kernel of the whole composition is just less than equal to kernel of one of the linear maps. And it's in fact equal to, the dimension is in fact equal to the kernel of the linear map T2, right? I think. Because S, well, for every element which S maps to inside the kernel of T2, then that will be a kernel of T2 composed with S. And in fact, since S is injective, that mapping preserves such a dimension. But that's maybe a bit of a stretch. So T2 is also has the same kernel dimension, or rather the same kernel as T1. And then T1 and T2 must have the same range, I guess. No, that's they have the same dimensional range, but it's not the same. Okay, I need to think about this some more. Perhaps I can use some double containment methods, but I think that's perhaps not such a bad idea.